Okay, so our next unit is probability, and today's lesson is an intro to that, the types of probabilities, and how to calculate them. So first we're going to go through some definitions about probability. So we're going to take a look at these definitions and apply them to a scenario where John is planning to perform a probability experiment by tossing 2 coins 100 times in order to determine his experimental probability of flipping 2 tails. So, and then he records the number of tails that actually occur. So one particular trial is one set of actions in an experiment. So in this scenario, that would be John flipping 2 coins and recording the number of tails. Probability experiment is conducting a series of identical trials and then recording the results. So I had listed recording the results in the trial. It doesn't really matter which spot that goes in, just as long as you're actually doing that. So in this case, it would be performing those 100 trials, flipping the 2 coins 100 times. A particular outcome is a possible result from one particular trial. So that could be, for instance, it could be 2 heads, it could be a head and a tail, it could be a tail and a head, or it could be 2 tails. Notice that I've listed both head and tail and head, even though you might think those are the same thing, but they can happen 2 separate ways. So it's important that we list it twice if we're listing all the outcomes. You may not need to list all the outcomes. You might be asked to list specific outcomes or something like that as well. All of the outcomes put together is what is called the sample space. And so we often actually write that in set notation. And we can use short forms like this, that's fine. Again, notice that I've listed both of these. So the kind of order matters in this case. It's not necessarily particularly in order, but the fact that that can happen in 2 different ways is really important. The random variable is an actual numerical value that can be measured based on your trials. In this case, we are recording the number of tails. It's tails that we're actually interested in. The random variable is generally represented by a capital X, and in this case, it can take on the values 0, 1, or 2. I don't list 1 twice there because it's the same random variable. It can just happen more than one way, which is kind of interesting. And then for our event, that's what we particularly want to occur. So the particular value for the random variable. So in this case, we wanted the random variable to have 2 tails. So the random variable number of tails would be 2. Again, so our random variable x equals 2. We often define our event with a letter as well. So for this case of this note, we're going to use E to represent the particular event we're talking about, but you can kind of use whatever letter makes sense for the particular example. But in the formulas we're going to be looking at, we're going to use an E. So the different types of probability, there are 3 of them. So there's subjective, and that's just based on previous experiences. Knowledge is basically an estimate. Like I predict that, or my subjective probability for me having a salad for dinner is 70%. I've been having a lot of salads. I've got lots of salad stuff in the freezer or in the fridge, but I've got some other stuff too. The probability of me making a certain drive in disc golf could be 80%. It's a hole that I've played a lot. I'm pretty good at that hole. In general, I usually make it, things like that. So you would back it up with some reasoning and then give a percentage. Experimental or empirical probability is based on the results of an experiment. So flipping the coins, for example, if he did the 100 trials and he got 2 tails 30 times, his experimental probability would be 30 out of 100. So in this case, the formula for this would be experimental probability of a particular event occurring will be the number of ways for that particular event to occur over the number of total trials. Theoretical probability is based on your counting techniques from Unit 1. And that is then how many ways a particular outcome can occur, or how many ways a particular value of your random variable can occur. And so for theoretical probability, we just use a P. And again, probability for that event to occur is going to be the number of ways for that event to occur over your sample space, which is the number of ways for anything to occur. Again, notice both of these have the number of ways for your event to occur, but this one's from trials, so successful trials. And this one is theoretical outcomes that could happen. So theoretical outcomes. Okay, so they're both number of ways for your event to occur, but it's number of ways that it has already occurred versus number of ways that it is possible to occur. Okay, so let's take a look at an example. So a research group has given a trial drug to 450 lab rats. Significant decrease in brain cell deterioration was noted in 376 rats. So this was already noted, okay? It was already given. Trial drug was already given to 450 rats. So this is telling me that we're actually calculating experimental probability. So we can define our event if we would like, instead of writing all the words. So I could say, let the event E be the drug working. I could have also just put drug working in my brackets. That's fine as well. So probability of the event happening is equal to, and this is experimental probability, is equal to the number of trials where it worked over the total number of trials. Number of trials where it worked are 376 over 450 total trials. And then on your calculators, you actually have a fraction button. Hopefully you know about it already, but it is often like A and B over C. Sometimes it's X over Y, something like that. But it will reduce all your fractions for you, which is nice because fractions give you exact values without needing to round. So I end up getting 188 over 225 as my exact value for that. And in my calculation, I'm just going to leave it as fraction in reduced terms if possible. If it is not possible, like if the question gives you decimals and it's kind of really ugly numbers or something like that, then you can leave it as a decimal. But try and keep your answers as fractions, lowest terms, because they are exact. And then in my therefore statement, so therefore, the probability of the drug working is, this is where I'm going to convert that to a percentage, because our brains kind of work in percentage better, right? Like 188 over 225, in order for my brain to conceptualize what number that is, I actually convert it a little bit in my head, right? I'm like, oh, well, that's, I might convert it to a fraction I know about, so it's around 3/4. But I'm having to do those weird comparisons in my head, whereas the percentage is 83%. My brain has a pretty good idea of what 83% is. So when I round appropriately, it is 84%. Make sure you round properly. Okay, moving on. If we want to look at dice, we often look at what's called an outcome table, and you can use this for other things as well, but it's really handy. It lists the entire sample space. So everything inside here is my sample space. Those are all the possible outcomes that could occur. And there's 36 of them in there. The reason there's 36 is because there are 6 ways for me to roll one dice, and there are 6 ways for me to roll the other dice. Since it's an and, you end up multiplying 6 by 6 and get 36. It's also the area of the inside yellow box. Okay, and this can allow us to count how many ways different things are possible. So if I'm rolling 2 dice, for example, let's think, what is the most likely sum when rolling 2 dice? And why do you think that's the most likely sum? Okay, so hopefully you guys identified that 7 is the most likely sum. And the reason for that is because it has the most ways to happen. The most sets of dice that can make a sum of 7 occur. So if we look at the outcome table, we can highlight everything that's a sum of 7. So a 6 and a 1 make a sum of 7. So does a 1 and a 6, 5 and a 2, 2 and a 5, 3 and a 4, 4 and a 3. Those are, for sums, they're always going to be on diagonals like that. So that's just kind of a quick way to look at it. And when I'm using these outcome tables, I can just highlight in order to show my work for figuring out how many ways to do something, which is nice and handy. So I would suggest you make one of these outcome tables in your notes on just one big sheet of paper, and then just keep it at the front of your binder or something like that so that it's handy so you don't have to keep remaking them. So if we want to look at the probability for rolling a sum of 7, well, it's going to be the number of ways for me to get a sum of 7 over the total number of ways I can roll. So in this case, it's 6 over 36, which then reduces to 1 over 6. Not showing full communication in this because we just modeled it in one before. And we want to kind of just speed through this a little bit. What is the probability of rolling a sum greater than 9? I am going to show proper communication for this one just because I want to show how you can show a sum greater than 9. Again, I'm going to use a different color highlighter here. You can use different shapes or whatever, just some kind of way to make a legend. So sum greater than 9, well, 12 is greater than 9, 11 is greater than 9, 10 is greater than 9. That's it. It doesn't say greater than or equal to. So then my probability of getting a sum, I can use the sigma notation, the sum that we've used in stats, greater than 9. That's going to equal the number of ways for me to get a sum greater than 9 over the total in my sample space. And I ended up highlighting 6 there out of 36, which again happens to equal 1 out of 6. Probability of rolling at least 1 3 when rolling 2 dice. At least 1 3, well, all of these have a roll of 3, and all of these have a roll of 3. I'm counting the 3 3 because it has 1 3, it just also happens to have another 3. So that one I ended up highlighting 11 out of 36. Okay, moving on. If we look at the word probability, what's the probability of selecting a vowel? So that's just going to be probability of getting a vowel is going to equal the number of vowels over the number of letters. Now I can keep writing it in S, or I can just fill in what my S is, which is kind of helpful to kind of understand what's going on in the question. So the number of vowels, there are 1, 2, 3, 4 vowels. Over the number of letters, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 4 over 11 for that one, can't reduce it, so that's fine. Probability of selecting a B, well, there are 2 Bs, again, over 11 cards. Probability that B is not selected. Well, in the first unit, we learned a term called the complement. The complement is something not occurring. And that's just the inverse, kind of. It's like 100% minus. Remember that probability, we didn't talk about this on the first slide, but probability goes from 0 to 100%, or as a fraction or decimal, 0 to 1, which is really important. So the total probability is always going to be 1 of all the different outcomes. In this case, if we're looking at a B, you either select a B or you don't select a B. That needs to add to 100%. The complement plus the regular has to add to 100%. So if I want to know probability of not selecting a B, and we can use the line or the apostrophe to represent the complement, that's just going to equal 1 minus the probability of selecting a B. So then that equals 1 minus 2 11ths, which equals 9 11ths. And that's the probability of the complement. It started as an equation, so I have to continue as an equation. Okay, last piece, we're going to take a look at blackjack, and I'm actually going to ask that you pause the video right now, use everything that you've learned from this lesson, and try and calculate the probability of a blackjack. Actually, just before you do that, if you don't know what blackjack refers to, it's not getting a jack that is black. So blackjack is a very common casino card game. It is the theme of the movie 21. It's also in Rain Man and The Hangover when they go and count cards. To get a blackjack, you have to get an ace and a card worth 10. So think about how many different cards there are that are worth 10. The face cards are worth 10 and the 10s are worth 10. And you have to get that just with 2 cards. So I want you to pause this, try and calculate what is the probability of getting blackjack when dealt 2 cards. Go ahead. Pause now. Some of you haven't paused. Pause the video. Give it a try. Okay. Hopefully you paused. Here we go with the calculation. So the theoretical probability of getting a blackjack, let's actually define our event here. Because if I just write, again, blackjack, you might think I'm talking about getting a blackjack in particular. So I'm going to say the event, E, is being dealt blackjack with 2 cards. Okay, so probability of getting E is going to equal the number of ways for me to get E over the total in my sample space. So probability of getting E. For my event E to occur, I need an ace. So it's going to be a number of ways for me to get an ace. And multiply. I need a card worth 10. So 10, Jack, Queen, King are worth 10. So that's 4, but then there's 4 suits. So the number of ways for me to get a 10 value. No, 10 value is just 10 value. And that's going to end up being 16, but we'll do that on the next line. Over the number of ways for me to be dealt any 2 cards. So again, probability of my event. To get an ace, there are 4 aces in the deck. I just want to choose one of them. If we get in the habit of writing this down in choose notation, even when we're just choosing one, it'll help us in the long run because we won't always just be choosing one. To get my 10 value card, 16, choose one of those. The denominator, I'm now being dealt 2 cards. So 52 in the total deck. Oops. Choose 2 of them. That's the idea with that. Then we can actually go through and punch this in our calculator. So 4 times 16, well, that's 64. I don't need a calculator for that part. And then 52, choose 2, I think is 1326. But let me just, 1326, checked it in my calculator. And then again, I'm going to use my reduction of a fraction button, 64 over 1326 gives me 32 over 663. We leave our mathematical answer in a fraction that is reduced. And in our therefore, we convert it to a percentage because our brain works a little bit better as a percent. So therefore, the probability of being dealt blackjack is 32 divided by 13. Oh, no, sorry. 32 divided by 663 equals 4.8%. So say 5%. So it's actually pretty high, right? That's about 1 in 20 you think you get a blackjack. Wonder subjective probability if that's what you would have guessed ahead of time if we had thought to make a guess. Okay, that is the end of the lesson for today. So just follow along on the Google Classroom post for what the practice work is.